Good morning and good evening in Korea. At first, I'd like to thank jury and committee for being here today and the opportunity to present my doctoral work today. Thank you so much. My name is Hyon Kim. My dissertation is titled Piano Performance Analysis via Dynamics Estimation and Feedback Classification. In this defense, I will summarize the background, methodology, and key contributions from my thesis. The structure of the thesis is structured as this. Today, I'm going to focus on chapter 1, 3, 4, and 5, focusing on talking the background of the research and node-level MIDI velocity estimation, context-dependent dynamics marking estimation, and multiple feedback and mark tags classifications. Throughout this defense, this icon indicates the new finding based on my work in the thesis. Okay, let me introduce the background of this research. In a typical situation in the music education, students and their teachers normally employ the feedback approach to improve and to acquire their skills. Feedback approach requires to have common goals between students and the teachers, such as playing a new excerpt and passing exam or attain new technique, etc., etc. And towards their goal, teachers and students have to find a gap, such as detect mistakes or fingering body posture is wrong or piano expressiveness too plain or too dynamic, etc. And after finding a gap, teachers should give the feedback to the students to improve, such as showing the model performance, like best performance from them, from teachers, or provide the HOs or training menus for students to improve. And in computational methods to support this feedback approach, currently we have these points to support. Piano performance itself consists of two main pillars, such as tempo or rhythm, or dynamics and pitch. Those 3 points are main points to evaluate piano performance itself. And tempo rhythm is done by the onset and offset detection. And dynamics is currently done by the overall loudness detection or transition analysis. And pitch is in piano case, pitch is already fixed. So finding the wrongly pressed keys in polyphonic manner, because piano has so many keys, which is polyphonic. And another important things to evaluate is fingering and body posture, like wrong fingering posture or wrong fingering numbers, etc., are so important to look into. And to give a feedback, overall feedback construction is currently available, like end-to-end performance evaluation by grading from pass to A+, or scale from 0 to 10. Yes. Although we have these state-of-the-art technologies, there are still gaps towards the actual use case scenario, which is node-level loudness estimation is not really explored, and it's disregarded often. Although in piano performance, node-level loudness is very important to construct melody line or voicing or accompaniment and expressiveness across the genres, not only classic or jazz, but across the genres. These facts are proven by previous works of these people. And so node-level analysis in terms of dynamics is very, very important topic to tackle too. And another topic to dive into is the subjective interpretation of dynamics transition. So all the pianists performs the dynamics markings or expressiveness very differently. But still, there's a trend, which is good or bad. So we have to find what's the overall transition of dynamics throughout the excerpt. In terms of the feedback analysis, we have to tackle to the detailed feedback, not scaled from pass to A+ or 0 to 10, like granular and detailed feedback to indicate which part is wrong or bad to improve. So in this research, those 3 points are going to be tackled. To tackle those 3 problems, I created 2 research topics. And topic 1 is the node-level MIDI velocity estimation and dynamics markings estimation with score information. This is written in chapter 3 and 4 in the thesis. Let me clearly define what is MIDI velocity. MIDI velocity represents the key strike speed encoded as integer value ranged from 0 to 127. The bigger number, the louder or faster speed. This MIDI velocity correlates the loudness itself of the piano performance for each key. So after detecting the MIDI velocity of each key, translates the aggregate MIDI velocity into the dynamics markings. That's the second part of this topic 1. And for topic 2, multiple feedback and the mark tagging is researched and tackled into. By this research, I developed a model to tag issues and marks in more granular way by one deep neural network. Let's go into the research topic 1, node level MIDI velocity estimation and DM estimation with score information. In this presentation, DM indicates the dynamics markings. Okay, so I divided the topic 1 into 2 steps, meaning that developed 2 models. Model 1, intake, score and note information, and performance audio together, and the output MIDI velocity for each note, only for performance notes. And for model 2, from the detected MIDI velocities for each note translates into the dynamics markings. These 2 steps were developed in this topic 1. Let's define the problem clearly. By taking performance audio and note frame information, estimate MIDI velocity for each performance note. This topic is previously researched by these people, and Dr. Jung is the jury here today. He also tackled this problem previously. And there's also another paper try to detect MIDI velocity by the DNN method. First, I would like to introduce technical aspects of this DNN network, how to take score information and audio information together, even though those are different modality. I employed feature-wise linear modulation, which is called film. Film is widely used in the natural language processing and image processing. Film in this research by the parrots takes the natural language as a condition to be inserted into the base DNN network, which is image processing, which is for image processing. Then this condition helps this base network to detect target object in the image. This is proven fact that this conditioning improves the object detection accuracy. So I employed this technique to my problem, apply film to our problems, which is score information is a condition to be inserted into the MIDI, to be inserted into the DNN base network. And trying to integrate those 2 modalities into one. And film conditioning has the learnable DNN network by itself, which is this one, film generator network. So conditions goes into this, not too deep, but depending on the design of this parameter generator, generates the film conditioning parameter, then it applies to the latent space of this main network. This is a technical background of the how to apply the film to integrate 2 modalities. This is the model configuration to tackle to the problem. Data sets that I used are Maestro data set, which is a data set of classic music excerpt performed by competitors of Yamaha E competition. And it's recorded on the Yamaha Disclavier. And testing set I used is the silent music data set. This is because the benchmark model, like the previous work, used this data set for evaluation of the model. So I also used this test data set to make a fair comparison against the previous work. This is also consists of classic music recorded on Yamaha Disclavia. Then input is, as I mentioned, performance audio and note frames. Output is MIDI velocity for each note, scaled from 0 to 127. Throughout this development, I developed 3 models. One is the CNN GRU with film. Another one is diffusion-based model. And another one is unit and attention gate-based model. And loss functions, I used 2 loss functions because I tested several loss functions, but these loss functions works the best. For this diffusion model, I used the L2 loss functions. And for CNN GRU and unit attention gates, I used the combination of L1 loss and BCE loss. I tested L1 loss and BCE loss separately, but they didn't work as well as this combination. The reason why this combination works the best for these models is the BCE loss is made for detecting classification task, binary classification task, which is keys pressed or not, which keys pressed or not. So each key, like 88 keys on the piano, each key has the 0 or 1 activation for performed note to judge performed note or not. Then L1 loss is for the regression model. So this calculates the how the gap is big between estimated MIDI velocity value and the ground truth MIDI velocity value. So this combination works the best for these functions. And for evaluation, note level error is looked into. So average of the aggregated or summation of note error is defined as error in this development. So these are like overall view of the architecture of 3 networks. The reason why those 3 networks are chosen is CNN GRU model is famous for working for the transcription model by convolutional neural network. And diffbel is also known for transcription model. Then unit and attention gate is known for the source separation model, and also multi-pitch detection model. So each 3 models has the like strengths to tackle to this problem. So I chose the 3 models to try out. Then I set benchmark models. So these 2 models are benchmark for my development. And one of them is DNN-based model, which is developed by Sony. And another one is non-negative matrix factorization model developed by Dr. Jung. Before going into the detailed architecture, I'd like to explain how I inserted film conditioning into the base models, the 3 models. And there are also like matching of how to insert film vectors into the main network. So the 2 ways are tested. One of them is the one-to-one operation, which means the film generator generates as many parameters as main network, latent space of main network have. So it's one-to-one correspondence between conditioning elements and the elements in latent space. Another operation is the one-to-all operation, which is used by CNN GRU model. And it creates the one element to control or to condition one vector in the latent space. So dimension of film conditioning vector is way lower than main network, latent space of network. So I tested those 2 methods and chose the better performing method to insert this film conditioning vector. Yes. Let's look into only one model a little bit in detail. I like to introduce the unit-based model. For the unit-based model, there are 2 stages in the network. One is the encoder stage. Second is the decoder stage. So during the encoder stage, performance audio and the note frame information got encoded and the conditioned together and merged into one. And those film conditioning network, I chose the convolutional block, this part. This convolutional block has the same structure of the convolutional block to encode the audio information. The reason why I chose this structure is those two information, note frame and the log mail spectrogram, having the similar information as a content. So I chose a similar way to process the two information would be appropriate to insert or combine together. Then film conditioning happens each block between those convolutional blocks. And after encoding the information, I use the attention gate between each blocks of convolutional blocks. This attention gate is supposed to look into what parts of latent space vector are important, what elements are important, what should we look into. So I put the assumption that this attention gate should look into the detected key and the velocity information in the latent space itself. So this is the chosen final structure of the unit and the attention gate. This is the results of the MIDI velocity estimation task. Among the proposed model, the unit with film and attention gate work the best. Error is 9.9 out of 127, the biggest error. And node detection rate is almost 90%. And this is comparable result to the state-of-the-art model, which is error is 9.9, and but the node detection rate is lower than the unit model, proposed model. This actually implies that this unit model is more robust across the data set because Sony HFT model used the same test set from Maestro, but once test set is changed, the accuracy of the node detection rate went down. So this model is not as robust as the unit model across the testing data set. However, NMF model is surpassing the way better results in terms of the MIDI velocity estimation for each node. But there's a pro and cons between DNN-based model and non-negative matrix factorization-based model. That is, NMF optimizes model parameters for each excerpt. So we have to train the NMF model for one by one in the test data. But this DNN-based model is generic across the all excerpts. So this is like biggest pro and cons. So I would say in the DNA network is more generic to classic music, but not fitted to each excerpt, such as non-negative matrix factorization. Let's look into the ablation study a little bit. And this is the visualization of the output from the unit model. So this is the ground truth, MIDI row, and this is the estimated with film information, film conditioning. This is estimated result without score information. So once we insert the score information, node detection rate gets way higher, and the result is way closer to the ground truth. This phenomenon could be observed, is observed across the output. So node detection rate is way better after inserting the score information. This can be seen from the number 2, from these results. Then when we look into the effect of attention gate, it's still marginal. It didn't perform as I expected, but still it improves the error slightly, but it's very, very marginal compared to film conditioning. I think the reason why attention gate didn't really perform as I expected is this attention gate, first of all, it was really shallow. I mean, if we use the more complicated attention structure, such as a transformer, it could have improved this result. Then let's go into the error analysis, where we make mistakes. So I allocated MIDI velocity estimation results into each bin of MIDI velocity and bin of pitch, and bin of sustain pedal on and off. So this blue line indicates the distribution of the nodes in training data. So most of training data is performed in between velocity 40 to 100. And around here, like very soft nodes and very loud nodes are quite rare in the test data. So if we cannot see a lot of data in the, during the training phase, the model makes a lot of mistakes. Same goes to the pitch bends here, like pitch, like lower pitch and higher pitch that are not really appearing in the data set. The model makes mistake. But a surprising fact is that I thought pedal affects the results a lot. But even if pedal is activated on and not activated, sustain pedal is not activated, the error is not significantly increased or decreased. So yeah, sustain pedal doesn't really matter for MIDI velocity estimation task in these models. Yes, that's all for the MIDI velocity estimation task. As a summary, this MIDI velocity estimation model, main takeaways are exploration of DNN-based models and the achieved SOTA results in node level MIDI velocity estimation by DNN methods, and the data distribution management is needed as future work to tackle to this kind of error. Now we move on to the model 2. After detecting the MIDI velocity, is it possible to find dynamics markings as an aggregated MIDI velocity value? Yes. Let's define the problem clearly. Create a map between aggregated MIDI velocities and DMs in order to capture subjective transition in dynamics on piano performance. Related work is the audio to DM translation done by Dr. Catarina Costa, jury here today. So this is the visualization of the MIDI velocity transition. So I took the average MIDI velocity within 4 beats after each dynamics markings appearing this excerpt by Schubert. So there are the 22 professional performances is recorded in MIDI. And each pianist plays it differently for each dynamics markings here. Mezzo forte, pianissimo, mezzo forte. This order is the order of appearance in the excerpt. So what we can see from here is the each professional pianist plays very different MIDI velocity. However, we can see the trend in the MIDI velocity transition. So is it possible to capture by the model? What this graph indicates is the MIDI velocity is capable to capture the transition of each pianist in an excerpt. Now here is another interesting phenomena. This is the MIDI velocity transition in Mozart K331 excerpt. Appearing dynamics markings OP in the excerpt. However, there's still a trend for same P, piano, as the dynamics markings. There's another dynamics markings in between here, like crescendo, decrescendo, or forzando, etc. But if you look at same P, appearance, order of appearance in the excerpt, there's still trend, which is not as visible as before, but still trend for each pianist. Yes, to tackle to this problem, I employed the mask language model. What is the mask language model? It is widely used method to create the model to understand natural language. Mask language model masks some kind of word, some word or token in text. And based on the context information, this model predicts or estimates what kind of word or token can be inserted in here. So I use this idea to estimate dynamics markings based on performed note MIDI velocity as context. So yeah, I masked dynamics markings in a score and gave the model these performed notes with velocity. To make this happen, I created a data set. So those three data set provides the performed MIDI and the score information, which is written in music XML. And these data set have match file to bridge between performance MIDI and the score information on note level. So each note performed on score is tagged from the music XML by the match file. So we can find the positioning of the dynamics markings from this structure of the data set. So I combined those three data sets to make this development happen. At the end, and these three data sets are performed by competitive pianists or professional pianists. So these pianists should follow dynamics markings, not randomly, but based on their interpretation. And at the end, there are about 1K usable performance and the 78K dynamics markings in the data set. Some kind of data cleaning was needed, like tight note, grace note, which is not performed in the MIDI, MIDI, performance MIDI row. So these kind of notes are removed to be cleaned up. And this is the distribution of the dynamics markings in the data set. It's very unbalanced and skewed. And so I combined similar dynamics markings and made a group. For example, pianissimo is combined together with the pianissimo, like 4 Ps, and made into one group. And same goes to the other like 3 dynamics markings. So these are grouped into one for the simplicity. And I also created 2 dynamics marking groups for the model developments. One of them, the constant dynamic markings, which can be ordered based on the loudness from pianissimo to fortissimo. Then another groups for the development is I included the non-constant dynamics markings, which is crescendo, decrescendo, fortepiano, rinforzando, and forzando. Those are also combined into one together with constant dynamic markings. This is how I created the sequence of combination of performance MIDI row and music XML. By using the match file, as I mentioned, we can find the positioning of dynamics markings and notes. So I created the one sequence of the combined information of performance MIDI row and music XML. Here, of course, we can take MIDI velocity information. And I created the vocabulary dictionary to translate into the serialized data into machine-readable format. This is the detailed structure of the sequence. For note information, we have this information, distance towards the dynamics markings, how far it is in the beat, and the pitch information and note duration, velocity, stuff, where it is it on upper stuff or lower stuff, or pedal, sustained pedal information, is on or off, and duration, meaning that the note exists before or after of the dynamics markings. And for each dynamics markings, serialized dynamics markings, we have type, which is fortepiano is the name of the dynamic markings, and stuff, and where it is. And token dictionary is created as here. Mask token is one, which is normal setup in the mask language model. Then I created tokens for each dynamic markings up to 14, and after that stuff indications and pedal, relation, pitch, velocity. In total, for expanded DM groups, there are 278 tokens. And for constant dynamics markings group, there's five dynamics marking nests, so it's 273 tokens in the dictionary to translate. And this is the model configuration. And RoBERTa model is employed because it is one of the most well-known model for mask language model. But original model configuration for natural language processing did not work at all for this setup. This is because token dictionary is way smaller than the natural language processing. For example, like normal natural language model for mask language processing, the dictionary is about 10K tokens, but we only have about 300 tokens. So I had to reconfigure this model size, but it's not clear how to make it smaller. But I did some kind of experiments, and the best configuration of this model is this size. Hidden size is 512, and hidden layer 6, etc., etc. So I tested smaller model, but it did not work as well as this configuration. And I explored 3 loss functions: categorical cross entropy, which is often used for the multi-class classification task, and weighted categorical cross entropy, which takes this matrix for penalizing estimation if the estimation is way far away than the ground truth. So if ground truth is pianissimo, then fortissimo is predicted. Penalty 7 is applied to the loss function, like token distance. And MSE is also like coming from mean square error, is also coming from the same idea, penalizing model based on the estimation distance. So these 3 loss functions are tested. And I only masked the dynamics markings because it is what we are interested in. Then 75% of dynamics markings were masked so that we can see the relativity against the shown dynamics markings and see the more trends more clearly towards the model. And I conducted ablation study as well. As I mentioned, 2 DM groups and the with and without pitch information. So there's a duplicate performance on the same excerpt. So model might learn pitch transition, not dynamic transition in velocity. So I removed pitch information. There's a research saying that pitch information also matters the perceptual loudness. So I also wanted to see how the result changes if pitch information is removed 100%. So this ablation study is conducted as well. And evaluation is done by the correct detection ratio for each dynamics markings, and I took the average of them. Before showing the result, I'd like to go through current baseline of the mapping. Like Logic Pro 9 or some software has the, their own definition between MIDI velocities and the dynamics markings. So I mapped those 1K piano performances based on these definitions. However, the accuracy was kind of low. This indicates the actual pianists do not really perform their interpretation, subjective interpretation, based on these hard-coded definition of MIDI velocities. Accuracy is about 15%, and the accuracy including one neighbor, which is if fortissimo is ground truth, like here, and it, including forte and fortissimo as well as an accuracy. But even if we include the one neighbor, the accuracy is 35%. So here's the results about constant dynamics markings estimation. So accuracy for all loss function setup exceeded the baseline hard-coded definition. And the, including one neighbor accuracy, its most performing accuracy is the weighted cross entropy, about 73%. And there are some dynamic markings that model struggles to estimate, which is mezzo piano and mezzo forte. This is mainly, I think, the reason. This is because those dynamics markings do not really appear in the training data set. Like it consists only 0.4% and 2.7% in the training data. It's difficult for model to correctly detect these rare tokens. Ablation study And pitch, if we remove the pitch tokens, yes, it got reduced the accuracy. But looking at the one neighbor accuracy, it's still, I mean, comparable towards the CCE. So it's still showing the like tendency to detect dynamic markings purely based on MIDI velocity transition. Here's the result of the expanded dynamics marking group. And accuracy is the 60%, which is way better than the constant dynamic markings. However, there are some, I mean, confusing dynamics markings for the model, which is forzando, rinforzando, forte piano, or crescendo. It's like model is confused for the very short and long increments or, I mean, decrements of the loudness. Like transition is still a little bit confusing, even confusing for human ear, I think. Then yeah, same as constant DM group, CCE, weighted CCE works the best. Same as pitch tokens. Yes. As a summary of the dynamics markings detection, this is the first research of the creating model to map MIDI velocity, aggregated MIDI velocity to dynamics markings by masked language model methods. And the dataset correction, I combined 3 datasets and created token dictionary for this task purposes. And model configuration exploration and the developed model to detect the transition of the dynamics markings. Now we're going to topic 2, multiple feedback and mark tagging. Let's define, again, the program clearly. Create a model that processes performance audio and describes the performance by tagging marks and performance issues across the multiple aspects. So this is, there's a previous work done by Palmer, but this is the overall like scoring or marking, like from 0 to 10, scaled from 0 to 10. And another task done previously is the timbre classification in violin performance done by Dr. Rafael Ramirez, jury here today. So this project is done by the music education company and protected by any non-disclosure agreement. So I cannot really disclose the detail of the metadata or like model structure, etc. But I like to go through the overall picture of the development. So dataset size about 2,600 performances separated from grade 1 to grade 6. And in the grade 1, 667 performances are included. So I separated grade 1 for model development and the entire grades from 1 to 6 for model development to see how difficulty affects towards the model. And these performances are tagged by examiners. One big group of tagging is the mark tagging, which is fluency mark, consists of fluency mark and the techniques and the communication. Fluency indicates the flow of constant key control, and the technique indicates the control on rhythm and pulse with flow of excerpt, which is like tempo-rated marking. And the communication is about stylistic control, interpretation, and expressive realization and delivery. That means expressiveness-related marking. So these are marked from 0 to 7, but here I binalized into 2 groups. If the mark is higher than the mark 5, it's considered as good tag. And if it's lower than 5, it's considered as bad. And for the feedback tagging for issues, to describe issues, dynamics issues, hesitation, flow issues, hurry, slow tempo issues, and the pulse issues are introduced. These issues indicates the, of course, dynamics issues indicates the loudness issues for each dynamics markings, and hesitation issues, and if students forget or memory is not really clear, then it stops, this tags applied. And Harris low tempo is global tempo issues. So if the tempo issues happens everywhere in the in their performance, in their in their interpretation, Harris low tempo issues are applied. And pulse issues, the local tempo issues. You play this part, only this part quite quick, then these tags can be added onto the performance. So all tags are also binarized. If its tags are detected, it's bad, considered as bad. If it's no tags, it means good. And this is the model configuration. And input is student performance audio, and output is mark tags and issue tags. So the flow of the model is that by taking the performance audio, it is transcribed into the MIDI data with velocity. And the MIDI information with velocity is processed by the CNN blocks to process MIDI for tag classification task. And loss function is a binary cross entropy is used for loss functions because it's a binary classification task. BCE is most suitable one here. And evaluation is the simply accuracy and the F1 score are applied for mark tagging. And here's the results. For grade 1, actually, the results shows very similar tendency on the grade 1 and all grades. All grades had the better model performance in general. I think this is because all grades has way bigger data set, 2.6K data set. When it comes to size of data set, grade 1 only has 600 data set. So excerpt performance, sorry. And yeah, as you can see, F1 score for good is generally good compared to the F1 bad, meaning that this model is quite lenient towards the student performance. So even if it detects the bad performance, the model tends to evaluate the student performance as good. Looking at weighted F1, this actually indicates the good data set is way bigger than the data set of bad, because like macro F1 is like macro F1 treats those two classes equally, but weighted F1 weights the bigger data set more. So it means if these numbers are good, bigger than the macro F1, it means data set to describe good performances are bigger. And when we look into the issue tags classification, for both data sets, dynamics issues are like performing best. But however, those tempo-rated tags to describe issues are like similar accuracies across the data set. This is because I think the model is still a little bit confused with the global or local tempo issues. It can like misclassifying these tags to each other. Yeah. As an indicator to see this model is working or not, F1 has a threshold 0.6 to describe model is working good or not. And for binary classification, about 0.7 to 0.8 is kind of a threshold to define this model is working good or not. And I would like to explain why this model is working a little bit lenient. So this is the entire distribution of the examination, not focusing on performances, but also written examination and interview, et cetera, et cetera. So like out of 100, we can see the sudden spike on certain points. This is actually edge cases of being judged as better mark or passing or failing exams. So this examiner's tendency to give the mercy points or grace markings onto student performance can be affected or introduced as a noise in the data set, meaning that looking at this, like F1 goods, the performing best in communication, but the worst in the bad for the bad performances, meaning that for detecting communication like markings, this model is most lenient. These models are very lenient, and the examiners can control the points on communication, which is expressiveness related points, because it's very subjective, and but the examiners cannot really control the points on the like written examination or the other examination. So this kind of noise should be cleaned up. We couldn't really see the what kind of data is in the data set or not, but yeah, as a next stage of the development, this kind of noise removal should be performed. Yes. As a summary, main contribution from this research is that exploration and showed that multiple issue and mark tagging by DNN methods, and the accuracy of the model is still promising considering the data size and distribution, and shows it's worth continuing this multi-feedback and multi-mark tagging program and the model development. Yes, I'd like to summarize this defense presentation. And as a contribution written in chapter 6 in the thesis, achieved the total result for MIDI velocity estimation by DNN methods, and the curated data set by combining performance MIDI and music XML and translated it into serialized data, and created token dictionary for the task. And I built a benchmark for the contextual dynamics markings estimation, because this is the first model to tackle to the task by a mask language model. And I developed multi-tag classification model for student performance written in chapter 5. And what's the application of this research? And I would like to propose these 4 points as a possible application. One of them is facilitation between student and teacher by visualization of the performance. Visualization is one of the best methods to realize students' performance by themselves. So visualization is very important, in this method enables their students to be visualized. And expressiveness and analysis, and by node level, not the entire overall dynamics transition. And yeah, MIDI velocity transition within the performance. And this kind of expressiveness-related work can be applied to generative music rendering with expressiveness together. And also, this research is only done on the classic music, but this can be expanded towards the other genres, like such as jazz or pops, because node level informations are also known as important to the other genres. Let me introduce the future work. As I said, genre expansion, because this is only done on the classic music, and robustness towards misalignment. This research is based on aligned setup, so which is not really like happening in the real use case scenario. So alignment should be tackled too. And exploration on DNN architectures for multimodality, like how to create the new conditioning network. Currently, I'm naming, like in the latest model, transformer to generate the conditioning is also explored. So that kind of direction would be promising to go for. And data distribution management, not to use the skewed data set that are used in this development. These are related publications from the thesis. Yeah, if you're interested, please go into these papers. Each paper is presented in the conferences and peer-reviewed. And before finishing my presentation, I extended my deepest gratitude to my co-authors and the collaborators. Yeah, successful and smooth completion of these projects are direct reflection of invaluable support and dedication from them. Yeah, I clearly acknowledge their contributions to the project in this defense. Thank you so much.